This example comes out of 10.3 composite functions. So in this example we're told f of x equals square root of x minus 4 and g of x equals x squared. We're asked to determine the composite functions either by doing f of g or by doing g of f. That part hopefully is a review of something you know from before. So f of g of x is going to equal the square root of x minus 4, but you substitute in x squared where the x used to be, since we're putting g of x into f. So there's our function. G of f, very much the same idea, except we're putting f into g, so we're going to have something being squared, and that something is f of x, so x minus 4, square root of x minus 4 being squared, which if you simplify that gives you just x minus 4. We could graph these, punch them into our calculator, stating the domain. Now the domain of f, hopefully even without a calculator we should be able to know this one. We have f of x equals the square root of x minus 4. So the domain is that x has to be greater or equal to 4. Otherwise that all real numbers are fine for decimals, fractions, whatever, but you better have a number equal or greater to 4, otherwise you'll be squaring a negative number, which doesn't work out. Now the domain of g is very simple because the domain of g is all real numbers. You can square any number you like. If g of x just equals x squared, then the domain of that is just x is an element of all real numbers, so anything goes. Now f of g is a little bit interesting because f of g, we said, is f of g of x is the square root of x squared minus 4. Well, again, you can't square root a negative number, so really what we're solving here to figure out what the domain is where is x squared minus 4 either greater or equal to 0, because you can square it 0, it's not a problem. I probably would start by factoring that and saying, okay, x minus 2 times x plus 2 has to be greater or equal to 0. I think in terms of a little number line here, negative 2, positive 2. A number to the left of negative 2, negative 3, negative 10, negative 1,000,000. If I put that in there, I'm going to have a negative times a negative, which gives me a positive, which is greater than or equal to 0. So any number to the left of negative 2 will be in my domain for that function. Number in between, easiest one to pick is 0. I'll have a negative times a positive. That means this is going to be negative. Anything between negative 2 and 2 is not in my domain. A number greater than 2 gives me a positive times a positive, and 2 and negative 2 are no problem because they do give me 0, which is allowed for this one. So the domain for this particular function is just that x either has to be less than or equal to negative 2, or x has to be greater or equal to 2. Other than that, all real numbers are good. If you looked at that on a graphing calculator, you would see a curve something to the effect of a curve going to the right, curve going to the left, and we did graph that way back in chapter 2 somewhere. Now the last one is interesting because if you just graph y equals x minus 4, g of f of x, it is tempting to say the domain is all real numbers because a slope of line, y-intercept of negative 4, it's tempting to say, oh, that graph looks like this, and it goes everywhere we want it to go. But realistically, even though the final simplified form is x minus 4, at some point we had the square root of x minus 4, and then we took that answer and squared it. So we still actually have the same restrictions that we had before for square root of x minus 4. X does need to be greater or equal to 4 for us to even have this expression anywhere in our question here. So the domain of this actually is dependent on not only the domain of the final answer, which has no restrictions on it whatsoever, but also the domain of the innermost function. And that's really why I chose this example, is when you're considering restrictions, you consider the restrictions on the inner function as well as the final composite function. And so kind of a good example that illustrated that.